Alrighty, everybody. It is currently Saturday, March 14th, 2026, and I am coming at you live from a world of subatomic particles that are crashing into each other and giving birth to energy. Because that's what we're talking about this episode. That's the basics of a nuclear reaction. Things crash into each other, create energy. We're going to be getting a little bit more into the nitty gritty of how exactly the energy is created, or I guess you can't really create energy. How the energy is transferred from one type of energy to another type of energy. I'm gonna be there's gonna be a lot of pauses for me to ramble about chemistry and nuclear chemistry and I guess physics and things of that nature that I know in all reality very little about compared to a normal, just regular, everyday, run of the mill person. I know a decent amount about it, but I mean, compare me to most anyone who has taken a class higher than chemistry 2, I know nothing. Even compare me to someone who has taken chemistry 2. Chemistry 2, college chemistry 2, that is the peak of my knowledge about chemical reactions and nuclear reactions and things like that. Which nuclear just means the nucleus of the atom. Usually in chemistry you're talking about the interactions between atoms. We're talking a little bit about this with nuclear chemistry, but specifically in nuclear chemistry we focus on the nucleus, which we'll talk about more later on. In this episode we're going to talk about how nuclear reactors transfer that energy. We're going to be talking about how they control those reactions, right? How they prevent basically the reactor from turning into a nuclear bomb. And then we're going to be talking about how it can turn into a nuclear bomb. You know what I mean? We're going to talk a little bit about Chernobyl, which Chernobyl wasn't so much an example of how dangerous nuclear reactors can be. It was more so an example of how the Soviets and really communists as a whole don't value human life. That's if the conclusion you come to about Chernobyl is that nuclear energy is bad, you need to reevaluate the situation because it's not about that. It's about how the Soviets would rather sacrifice hundreds of thousands, millions of human lives than not be corrupt pieces of shit who steal from their people constantly, which capitalists do that too, but at least we can acknowledge that. You know what I mean? At least the capitalist is like, yeah, we're stealing from the poor people. We're taking all their shit so that we can get rich. The communists, they hide behind a veil of equality and bureaucracy and things like that. The capitalists are straight up, we're stealing from you. Yeah, I'm a trillionaire and you can't afford insulin. Suck my dick. You know what I mean? Like I'm better than you. That's the idea of capitalism. But we are going to talk a little bit about Chernobyl. I've seen the show a couple of times, and in the show they do talk briefly about how the the situation came to unfold from a nuclear science perspective. Most of the show is just trying to convince communists that any amount of money and work and effort is worth human lives. Right? That's what most of the show is about. Most of the show is about how communist leaders don't value the lives of their people or anyone else. And how a few good people within that, greater institution of communism were trying to convince their leaders that no, we do need to spend the money or millions of people are going to die. And really, the communist leaders only agreed to it so that they didn't look bad on a world stage. If they could have contained it just to the point where it was massacring their own people, right? They would have done that. But they found out that it would have poisoned people outside of their country, and so they wouldn't have been able to lie about it and stuff like that. And so they did end up spending the money to prevent a complete, continental nuclear fallout, basically. Um, but yeah, we're only going to talk a little bit about Chernobyl. It's just it's very simple, actually. It's pretty, the chemistry behind it is not so simple, but how they ended up basically making a nuclear bomb out of a nuclear reactor, which is hard to do. You literally have to make some of the most retarded and short-sighted decisions humanly possible to for a thing like Chernobyl to happen. It literally has to be the perfect combination of incompetence, corruption, and bureaucracy. You know what I mean? Like having these bureaucratic leaders who don't really understand the nature of the thing that they have control over, making decisions about it, right? That's kind of the combination you have to have for an incident like Chernobyl to happen. There's been a few other nuclear meltdowns. The United States has had a couple. There was 3 Mile Island, which like no one, nothing happened with that one, and we're going to talk about why the safety measures that are in place for when a nuclear, because a nuclear meltdown, it sounds super bad. It does sound super bad, but in reality, it's it is bad. But if you have any any clue about what you're doing at all, if you have any care about the people around you, and you're willing to sacrifice a little bit of money, then they're really not that big of a deal. They could be, they can be that big of a deal. Um, but in terms of preventing a nuclear meltdown, there a lot of shit has to go wrong. A lot of shit has to go wrong. I guess we'll talk a little bit about Fukushima, which was another famous nuclear meltdown. There was a little bit more trouble there, but once again, that was just a shitstorm of everything going wrong, and not really, it wasn't really the fault of the people. A little bit, I think a little bit probably it was the fault of the people, but that was more so God. You can put that one on the big man upstairs. You know, Chernobyl, blame the communists for that one. That was entirely their fault. Fukushima, we'll put that one on the big man upstairs. Every once in a while, you just got to be like, yeah, it was God. God did it. Even if you're not a Christian or religious at all, sometimes you just got to you got to put it on the big man. You just got to be like, nope, it was God. There was nothing I could have done to prevent this thing. Or if something super good happens, you got to be like, there was no way I could have predicted this outcome at all. You just got to be like, it was the big man upstairs. You know. But let's talk about nuclear reactors. We're going to start off by talking about fission, which is it's the basis of how a nuclear reactor works. We're going to be talking about the interaction between subatomic particles and how that leads to the transfer of energy from one kind to energy that we can use. So, conventional thermal power stations use thermal energy released from burning fossil fuels to make steam and electricity. And nuclear power stations use the energy released from nuclear fission. So basically, every single type of power generation that we have, every significant type of power generation that we have, uses turbines. The only one that doesn't, that I can think of off the top of my head, is solar energy. Solar energy just converts energy from the sun straight into electricity. Don't know how it does it. It somehow hits a panel and then that turns into electricity. Don't ask me how that one works. But every other form of electricity, wind, hydroelectricity, traditional thermal electricity, nuclear electricity, all that stuff uses turbines. And basically what a turbine is there's a stick, and on the end of the stick there's a magnet, right? And so that spins, and around the stick, or around the magnet basically, there is a bunch of copper wire. It's not touching the magnet. It's basically like a donut. Think of it like a donut. The magnet's in the middle of the donut and it's spinning, but it's not actually touching the copper wire. And that when it spins, somehow the interaction between the poles and the copper wire, somehow electricity comes out of that. And so there's a few different ways to get it to spin. Um, Nuclear energy and thermal energy, traditional thermal fossil fuel energy, uses steam. Basically, if you've ever seen like a water wheel or anything like that, like in an old medieval village, when they have like the wheel on the river and the current of the river spins the wheel, and then attached to that wheel is an axle which like grinds flour or whatever. Replace the water with steam, and that's basically how nuclear energy and traditional fossil fuel energy works. It boils a bunch of water, that spins a wheel. Attached to the wheel is an axle, and attached to that axle is a magnet, and then surrounding that magnet is a bunch of copper wire. And when the magnet spins, it somehow moves electrons within the copper wire, and that creates electricity. It's all burning steam, or it's all boiling water creating steam, and then that steam spins a wheel. That's basically how we get all of our shit. And then you have things like wind and hydroelectricity. In wind, it's the wind is what spins that axle and therefore the magnet. In hydroelectricity, it's the current of the water. That's what spins the axle and therefore the magnet, which creates electricity. That's really our only way of generating electricity. And it hasn't changed in, I mean, well over 100 years. For well over 100 years, our main way of generating electricity is spinning a magnet that's inside a donut of copper wire. Pretty more than 100 years. I don't know when the turbine was invented, but it was well over 100 years ago. And so nuclear fission. Nuclear fission, you can kind of think of it as like the fire, the burning of the coal or the natural gas or whatever. It's thermal energy. Nuclear fission turns the energy that holds an atom together into thermal energy. So only certain very large atoms like uranium and plutonium, the typical radioactive atoms that you think of, can undergo fission because their nuclei have so many protons and neutrons, which makes them unstable. So basically, radioactive material is radioactive because it's so big that it can't hold itself together. This is related to E equals mc squared. If you've ever wondered what E equals mc squared is, it's the bonding energy of the atom. That's what E equals, and then m is like the expected mass of the proton minus the actual, or the expected mass of the nucleus minus the actual mass of the nucleus, and then c is the speed of light. I don't know how the speed of light is involved in all this, but this is E equals mc squared right here. Basically. Fuck, dude, my brain is fried. My brain is fried. My roommate decided to stay up until 3 in the morning last night playing video games and screaming as loud as he could. Not even my roommate, my dorm mate, who lives not across the hall, but we have like this middle living room area and then 2 dorm rooms on either side. He lives in the other dorm room, and he was screaming until 3 in the morning. So I'm a little bit tired. My brain is a little bit fried, but I'm going to try to explain this as best as possible. Basically, all you have to know about radioactive material is that it's super unstable because it's so big, right? And that when it breaks up, that creates thermal energy. Okay? They're unstable. So you first start with a heavy unstable atom like uranium 235, which is an isotope. I don't remember exactly how that works, but whatever. Uranium 235, it's really big, has a ton of neutrons and protons in its nucleus. And the way an atom is set up, if you don't know, it's a bunch of neutrons and protons in the middle, and then it's surrounded by electrons. And neutrons have no charge. They don't, you can either have a positive charge or a negative charge. Think of it like a magnet. Electrons have a negative charge, which is, we'll just call that the south end of the magnet. And then protons have a positive charge, which we'll call the north end of the magnet. And so, yeah, that'll come into account later. So just remember that. And so you have this unstable uranium-235 atom, which is then hit by a neutron, which is released from another unstable atom nearby, and this turns it into uranium-236, and the nucleus stretches and becomes unstable. So the charge is important because, say, if it was a proton that got released, it wouldn't be able to hit the nucleus because remember, an electron is basically the south end of a magnet, and a proton is basically the north end of a magnet. And so if you have the north end of a magnet and you throw it at the south end of a magnet, what's going to happen? It's going to stick together. So that wall of electrons would basically catch a proton. But since it's a neutron, it has no charge. It passes right through that magnet field around the atom and hits the nucleus, and that makes it unstable. So temporarily, we do have a uranium 236 atom. Yeah, that's where we're at so far. We have something that's already unstable, and it's unstable because it's so big, and then it gets even bigger, and so it's stretching, it's doing all that stuff. So now the uranium 236 atom is vibrating, and the electrostatic repulsion between the protons overwhelms the strong nuclear force, and the nucleus splits into two smaller nuclei called fission fragments. This is where the energy gets released. Energy gets released. There's also some radiation and stuff like that, but this is how our energy is created. Neutron passes through that magnet force field around the atom, hits the atom. The atom is already big. The atom already wants to break up. It already naturally does break up. This is called decay. And that's how the reaction gets started, is that one atom decays, sends out a neutron, and just speeds up the decay, basically. And so hits this atom breaks up, becomes unstable and stuff first, but that's only for a little bit. We don't really have to worry about that part of it. That's not really super important to creating the thermal energy. Hits the atom. Atom's already big as fuck. You can think of it like almost like a laxative, right? Let's say you ate a bunch of spicy Chinese hot pot or whatever, right? You ate some Szechuan hot pot. You're already bubbling and stuff. You're already about to blow. Some energy is already about to come out of your asshole, right? That's kinetic energy. When you have diarrhea, you could use diarrhea theoretically to turn a turbine, right? So think of your belly, your like intestines and stuff. They're bubbling. They're full of spicy Chengdu hot pot. And then this neutron that's coming in, that's like a laxative. And it's gonna cause the explosion, and a bunch of energy is gonna be released out of your asshole. That's, I don't know. I got laxatives on the mind. I talked about it in the current events episode. But that's how we can think of our atom in this situation. And it passes right through that force field. And so this breaking up is called fission, and it releases a huge amount of energy, radiation, and it releases 2 to 3 neutrons, which go on and break up more nuclei. This is the basis of how a nuclear reactor works, or how the energy is created. The thermal energy is created in a nuclear reactor. Is you have one thing. I'm going to try to get this cleared by my. You have a bunch of unstable stuff together. One of the unstable things goes it's a mosh pit. Is essentially what we have here. It's a mosh pit. One guy. It's a bunch of pissed off like white teenagers who hate their stepdad, and they're all in a mosh pit at like a Limp Bizkit concert or whatever. And one kid gets really angry, punches a guy in the face. That guy gets super angry, punches another guy in the face. Next thing you know, everyone's punching each other in the face. That's a nuclear reaction, basically. And this is the chain reaction. And how do you slow it down? We're going to be talking about how you slow it down a little bit later on. But this is our nuclear reaction. It's basically a bunch of kids punching each other in the face. They're getting more angry. They're getting more heated up, you know what I mean? And they're just all punching each other releasing a bunch of energy, right? When you're punching someone and you're working out like that, when you're doing a physical activity like that, your body starts to get hot and you boil some water. Is what's going on here. So the fire of a nuclear reactor is a bunch of neutrons flying around causing fission, and then from that fission even more neutrons come out, which causes even more fission, which boils water and turns a turbine. Is what we have going on here. Right? I explained it with a mosh pit, maybe a mosh pit. I've never been inside one, but I've seen a few funny videos online of people punching each other in the face and like doing crouching tiger, hidden dragon moves in mosh pits where they're like jumping up in the air and like kicking a guy in the chin and stuff like that. I explained it like a mosh pit. I think maybe that's a more relatable way to put it. And then the individual instability of the atom is your intestines being full of spicy Chengdu hot pot and then a laxative coming in there and causing an explosion of diarrhea. So this whole fission chain reaction goes on in the core. In coolant, which is usually water, but sometimes it's a gas or a liquid metal or molten salt, is used. And it's going through pipes and stuff that are basically wrapped around the core. And it's going through there and it's absorbing the heat from this nuclear reaction. And this is going to be important later on when we're talking about meltdowns, because it's kind of the basis of a meltdown. But anyway, the coolant goes around the fission reaction and absorbs all the heat that's being released from that fission reaction. And it's going around in like pipes and stuff. It's not actually touching any of the uranium or plutonium or anything like that. It's in pipes. And even the uranium and the plutonium, all that is in metal rods. So in a nuclear reactor, you have control rods, which slow down the reaction. You have nuclear moderator rods, which speed up the reaction. And then you have fuel rods. And these fuel rods, you're imagining just like a stick of straight uranium, like a glowing green stick out of The Simpsons or something like that. That's not what it looks like. It's like a metal rod. It's probably some kind of steel, like some high grade steel or maybe titanium or something like that. I don't really know. But it's a pipe. And in that pipe is a bunch of pellets of uranium or plutonium. And then you also have liquid reactors that use thorium. I was going to try to talk about this thing called a fluoride thorium liquid reactor, but then by the end of this, I was like, we're already fucking cooked. I can barely get through explaining what an atom is. I have to fucking compare it to diarrhea. So I'm not even going to try to understand, let alone explain a liquid or a fluoride thorium liquid reactor. But I assume it's the same basic principles. Fission releases heat. That heat is then absorbed by water. And then what does the water do after that? So this coolant then leaves the core in pipes, which pass through vats of water. And this is called the second water system. The first water system is the coolant. And sometimes it's not water, but most of the time it is, which boils the water, which then creates steam for turbines. That's how a nuclear reactor works in essence. In its most, if you boil it down to what it is, fission creates heat. That heat is absorbed by water. That water goes through pipes, which go through a big vat of water, and then it heats up the water, boils it. That creates steam. Steam turns the turbine. Turbine makes electricity. That's basically how a nuclear reactor works in its most simple form. And you're probably wondering how this water in the pipes is able to boil the water, right? Because if the water in the pipes was boiling, then it would be turning into steam itself. These are like super pressurized. If you've ever used a pressure cooker before, the basic principle behind that is if you increase the pressure in a system, then you raise the boiling point. We've always been told the boiling point of water is 212 degrees Fahrenheit or 100 degrees Celsius. Well, that's at sea level. If you go to like a super high elevation, the boiling point of water decreases because all the boiling point is is the temperature at which water turns from a liquid to a vapor. But if you have less pressure pushing down on that water, right? In in our sea level example, that pressure is air pressure, because the air actually weighs it's 14 pounds per square inch, if I remember correctly, at sea level. And so if you go up higher, there's less air pushing down on that water. And so it's easier for the water to go from a liquid to a vapor. And so the inverse is true as well. If you go down below sea level, then the boiling point of water increases because there's more air pushing down on that surface of that water, and so it takes more energy for that water to escape. Almost is how I'd put it. And so they basically recreate that phenomena in a closed system, and they increase the pressure in that system so that the water can't turn to steam until it gets to like 700 degrees Fahrenheit or something like that. Like it gets really hot up in there, and that's how they're able to use water to boil water. It's pretty interesting how they figure that out. So in nuclear reactors, heat expands the fuel, which changes the neutron absorption, which slows down the reaction. So moderation of heat is important for keeping the reaction stable. And sometimes you actually have to end up speeding up the reaction because there's this thing, it's like the critical, I forget what it is. It's something involving the word critical, but it's basically the least amount of fission that you can have going on to keep the reaction going. Um and so if it gets too hot, then that doesn't actually mess with the nuclear reaction in and of itself, but it does mess with the fuel. And if the fuel expands, somehow changes neutron absorption, and then that slows down the reaction. So heat is also important. And when we're talking about Chernobyl, that'll kind of come into play a little bit, is that you'd imagine heat would speed up a reaction, right? Because that's how it works in chemical reactions and stuff like that. In a nuclear reaction, specifically in a nuclear reactor, heat slows down the reaction. So hotter it gets, the the more slow the reaction becomes. And you're probably thinking, then how does a fucking meltdown happen, right? Because you're imagining a meltdown is like things get super hot and they start to melt. But if things get super hot, then it's like the reaction would be so slow that nothing would be happening. But we'll, 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 we'll talk about it. We'll talk about it later. And so now we're going to start talking about how the reaction is controlled, how it's sped up and how it's slowed down and all that bullshit. So, in order to slow down or speed up a reaction, you have to control the neutron flux, which is basically the rate at which neutrons pass through a given area. You can also think of it as like how many neutrons are out there causing fission. Fusion is a whole different game. Fusion heat actually, I think, speeds up a fusion reaction. We're talking about fission though. Fusion is a whole different beast, a whole different animal that I have no idea about. I truly have no idea about fusion or how it works or the theories behind it or anything like that. But in fission, if you want to speed up a a fission reaction, you gotta get that neutron flux up. Think of just fuck it. There's a bunch of scientific like mathematical equations and shit that they use to explain neutron flux. I'm gonna explain it like this. Higher neutron flux means you have more neutrons flying around, which is causing more fission reactions. Lower neutron flux means you have less neutrons flying around, causing fission reactions. That's what our neutron flux is. It's just the amount of neutrons. I don't know why they call it flux. I mean, it does sound really cool, like some science fiction, Star Wars, Star Trek type shit, but they could have used a simpler word, I'll say. I think they were just trying to be nerdy scientists for the sake of being nerdy scientists, calling it a neutron flux. But neutron flux is just the amount of neutrons we have flying around, causing fission and stuff like that. And so you can increase the neutron flux or you can decrease the neutron flux. And there's There's a few ways to do that. Increasing the neutron flux, like I said, it's not actually increasing the amount of neutrons that are flying around, but it's increasing the amount of neutrons that are going through a given area. But it also does actually increase the amount of neutrons flying around. So I guess my simple explanation of it was right. And so most neutrons released in fission are emitted instantly, but delayed neutrons account for about 0.65% of neutrons in a fission reaction, and they can take milliseconds to minutes to release. So, in theory, you could like shut off a nuclear reactor completely, and you would still have a few delayed neutrons coming out, you know what I mean, like 2, 3 minutes later, and causing more fission to happen. There's also another thing that we're going to talk about called heat decay that would also continue a nuclear reaction even if the nuclear reactor shut down, but we're going to talk about that later. Delayed neutrons, they're not terribly important. They're just something that if you were a nuclear engineer, you have to keep that in mind. You have to keep delayed neutron reactions in mind because they're going to be there. They're going to be there no matter what. Sometimes they can take a little bit to come out. Sometimes they can take, you know what I mean? It happens almost instantly. For all intents and purposes, it happens instantly. Like I said, not super important for what we're talking about, but, if you're applying for jobs on Indeed right now and you see and you see nuclear reactor engineer, you're going to have to be taking delayed neutron release into account. You're also going to have to take neutron flux into account and stuff like that. This is a neutron based game. Like I said, I've taken Chem 2. I knew a little bit about nuclear reactors going into this. Didn't know it was this neutron based. It's all neutrons all the time. So now we're going to talk about how you speed that or how you slow that reaction down. So the fastest way of adjusting the speed of the reaction is through what's called control rods. Talked about a little bit about them earlier, which are made out of what's a type of material called a neutron poison, which are capable of absorbing massive amounts of neutrons. There's a few different materials that they use for control rods that are neutron poisons. There's boron. Boron's big. Boron's big in the nuclear reactor game. Not so much anymore. They still use it for this thing called a scram, which we'll talk about later. But boron used to be big back in the day. Still used a little bit, not as much anymore. The other main thing they use, I think, is cadmium. Cadmium is the other element that they use for control rods. Basically, these are elements that are super good at absorbing neutrons. That's all you need to know about control rods. And so they absorb all the neutrons, decrease the neutron flux, therefore decreasing the rate at which fission occurs within the core. That's what control rods do. Absorb neutrons. It's their whole job is just taking those neutrons on. You can think of them like a nose tackle, right? In traditional, the nose tackles aren't as big anymore in football, but you watch football from like the 80s or something like that, you're going to see a big old nose tackle. A big old just 300-pound dude whose job it is to absorb blocks from like the centers and the guards and stuff like that so the linebackers can go tackle the running backs. That's what a control rod is. Its whole job is to just absorb damage and just take that shit so that I guess there's really no linebackers in this situation, but they're like the nose tackle. Just absorb that damage, eat up blocks, so the linebackers can go and make their plays. Once again, there's no linebacker comparison in this situation, but these guys are the nose tackles. These guys are your Vince Wilforks. They're your, William the Refrigerator Perry, Casey Hampton, guys like that. That's who the control rod is. And so reactions can also be sped up by using neutron moderators, which are made of lighter atoms that don't absorb the neutrons but slow them down. And so you're probably thinking, you want the neutrons to go fast, right? You want the neutrons to be going fast so that they're hitting a bunch of, so that they have like an increased probability of hitting a uranium atom or plutonium atom or some sort of fuel atom and causing more fission, right? You're like, why do we want them to move slower? Moving slower doesn't increase their mass, right? Mass, what is it? Velocity equals speed times mass or some shit like that, or maybe inertia. I don't remember what it is. um, but slowing it down does seem counterintuitive. It seems counterintuitive. You'd imagine you'd want them to be moving quicker, kind of artificially increasing the neutron flux by having these neutrons pass through an area more. Because remember, that's what neutron flux actually is. Let's say you have like a 1 foot by 1 foot cube, right? Or 1 foot by 1 foot by 1 foot cube, right? And yeah, a neutron flux is just the amount of neutrons that go through that cube in like 10 seconds, let's say. That's what a neutron flux is. And so you'd think speeding it up would increase the neutron flux, but practically it doesn't. It doesn't practically increase the neutron flux. In in theory, the neutron flux is higher because obviously they're moving faster, and so they're moving through that area more. But in practice, it doesn't actually increase the neutron flux, and I'll explain why. So these slower neutrons are called thermal neutrons, and they have a higher likelihood of causing nuclear fission due to something called the fission cross section, which is the effective target section for the nucleus. I have no idea how this works. I talked to ChatGPT a little bit, and I asked it to explain a fission cross section. It didn't really do a good job of explaining it. It kept it pretty simple. It basically just said that a fission cross section is think of it like a target. And when you slow the neutrons down, the fission cross section for a uranium 235 atom, that target gets bigger somehow. Don't fucking ask me how. I don't know why, but it increases that target size. And so the neutron is going slower, right? And they're flying around a little bit slower and stuff like that. But that target gets so much bigger from the neutron being slower that it actually increases the likelihood of fission occurring. And so in our box example that we were talking about earlier, right, where you have that 1 foot by 1 foot by 1 foot box, when you slow the neutron down, that 1 foot by 1 foot by 1 foot box increases to like 3 feet by 3 feet by 3 feet by 3 feet, right? If that makes sense at all. The box gets bigger. And so in all, practical applications, the neutron flux actually increases when you slow down the speed of the neutron. And so these neutrons are bouncing off of neutron moderators. And these neutron moderators, one of the big ones that they use is graphite. And that's going to be important for when we're talking about Chernobyl a little bit later on. But graphite is a big neutron moderator. And remember, moderators speed up the reaction. They don't speed up the neutrons, they actually slow down the neutrons, but they speed up the reaction because the fission cross section increases when a neutron is going slower. That's how nuclear moderators work, or moderator rods, or whatever they're called. That's how they work. And so yeah, control rods slow it down, moderator rods speed it up. I don't know if the moderator rods are actually rods, but we're just going to pretend that they are because it's simpler that way. It's simpler to explain it that way. And so yeah, so in the atomic nuclei, and this might explain how the fission cross section increases, but I couldn't figure that out if this is how the fission cross section works. But atomic nuclei also have specific energy levels for neutrons they can absorb, and slower neutrons often fit these parameters better. So it's like throwing a football, right? If you're a quarterback, yeah, you can theoretically throw a football 50 miles an hour or something like that. But your receiver, depending on the receiver you have, that might bounce off his hands. He might not have quick enough hands to catch that 50-mile-per-hour, throw across the middle or whatever. And so you slow it down on purpose so that your receiver has a higher likelihood of catching it. That's how you can that's how I'm thinking, right? That's how I'm thinking of this um specific energy level that the unstable atom is able to absorb. And so maybe this is how the fission cross section increases, is that it has a higher likelihood of absorbing the neutron, and then, you know what I mean, when it absorbs that neutron, gets unstable, expands, fission occurs, energy is released, and you also have the fission fragments that we're going to talk about here. Those are important. That wasn't a one-off thing, so I hope you remember the fission fragments. um but yeah, so that might explain how the fission cross section practically increases when a neutron is going slower, is because a slower neutron is more likely to get absorbed. Once again, don't know if that's true. If you're taking a test or whatever, I could be wrong. I could be wrong. And I'm imagining most of this is not intelligible or understandable in any way, shape, or form. It really is fried my brain, dude. When I'm actually doing it, when I'm actually doing the notes, I understand it all. Like if I was doing a test or something and it was like write out how a nuclear reaction works, how a nuclear reactor works, I would get an A on that part of the test. But actually explaining it out loud and imagining someone who doesn't know shit about this, right? Let's say you went to college for like accounting or some shit. You don't know anything about this shit. You don't know anything about atoms or the structure of an atom or any of that shit. The charge of a neutron or a proton and E equals mc squared. You don't know about that shit. So I'm trying to explain it to someone who doesn't know anything about it. I'm trying my best. And that's where my brain really gets fried. And so, yeah. Moderator, fuck it. Fuck the explanation. Fuck the receiver comparison. Fuck the fission cross section. Fuck all that. Control rod, slow it down. Moderators, speed it up. That's all you gotta remember. In moderators, water is another big moderator that they use. I don't know how the fuck you use that, how you make a rod out of water, because if it's ice, it's just gonna melt instantly. Beyond me. Graphite is the big one. Graphite is the big one that they use, which that's just carbon. And carbon's a super stable element, I think. Yeah, carbon's super stable, and so it doesn't want to absorb that neutron like an unstable atom like uranium 235 would. Okay, we got it. Water's also super stable, and so it doesn't want to absorb that neutron like plutonium or whatever. And so you use that to like bounce the neutron, slow it down a little bit so that the fission cross section increases. The target size for that neutron to hit increases. All right. Okay, we got it. And so now we're going to be talking about fission fragments and how those affect the speed of the nuclear reaction. So two common fission fragments that are created include xenon 135, which is a neutron poison, and iodine 135, which decays into xenon 135. And these have to be taken into account by engineers. And so when that thing breaks up, it releases a bunch of energy and neutrons and stuff like that, but it also creates a new atom, right? Because all an atom is, or all an element is it's just a connection or a collection of protons and neutrons in a nucleus surrounded by an electron cloud. And really, you don't even need that electron cloud. Actually, what an atom is defined by the amount of protons it has, I think. So let's say like 12 protons is carbon. It's always going to be carbon, no matter the amount of electrons flying around, no matter the amount of neutrons that are in that nucleus as well. If there is 12 if there's 12 protons in a little collection, that's always going to be carbon. Not actually, that's just a theoretical example. And then let's say like 14 is oxygen. If there's 14 protons, that's always going to be oxygen, no matter the amount of neutrons or electrons or anything like that. It's always going to be oxygen. That's how elements work, from my understanding. So anyway, when the uranium atoms break up, or the plutonium atoms, specifically uranium is the big one that's used in nuclear reactors. It's also used in nuclear bombs. Nowadays, we use hydrogen in nuclear bombs somehow. I don't know how that works. But anyway, uranium, when it gets broken up by that fission reaction, creates a couple new elements. Sometimes it can be two new elements, sometimes it can be like three new elements, but it always creates new elements when it breaks up. One of the most common ones is xenon 135. And xenon 135, it's a neutron poison. It's hungry for neutrons. It says, give me all those neutrons. I want to eat it all up. You know, it's a hungry boy for neutrons. And so you have to take that into account when we're talking about the speed of fission in a nuclear reactor, right? Because if fission's going super fast, then you're creating a bunch of xenon. And when you create a bunch of xenon, that poisons the reactor because all the neutrons are getting absorbed by the xenon instead of hitting the other uranium 235 atoms. That would then, create energy and stuff like that. So that's important. And now we're going to talk a little bit about Chernobyl. So if shit goes to fuck, reactors have this thing called a scram button. Scram. It's spelled how you'd imagine scram is spelled. SCRAM. I think it's an acronym for something. I don't know what the acronym is, but it's called the scram button. And this inserts a large amount of poison into the reactor. This is where boron comes into account, like I was talking about. Boron control rods, they are still used a little bit, I think, but the big one is cadmium. But scram buttons, they put all the control rods into the thing, which absorb all the neutrons that are flying around. But the other thing they do is they'll just dump a ton of boron into the nuclear reactor. It's in the form of boric acid, which I think that's what borax is. I could be wrong. But they'll also, in addition to inserting all the control rods and pulling all the fuel rods out, they'll also just dump a fuck ton of boron into this reactor. So boron still a little bit important. Cadmium's our main guy, but boron's there if you need it. You know what I mean? It's not the main thing you want to be using for some reason. I don't know why. I guess cadmium is just a better poison for the reactors. I guess it absorbs more neutrons or something like that. But boron is also important because it'll dump in there during the scram. In the scram, there is a scram button, but also there's computers and shit inside the nuclear reactor, and if it suspects a meltdown at all, like if the temperature gets too high, it'll just be like, fuck it, better safe than sorry, dump a ton of boron into there. And so in the Chernobyl reactor, the scram button was called AZ5. If you've seen the show, they all have British accents, and so they all say AZ5. It's Z. Z, that's a retarded way of saying Z. It's AZ5 was the scram button in the Chernobyl reactor. And basically in the Chernobyl reactor, they slowed down the reaction a whole bunch, and then they sped it right the fuck up. That's all you have to know. And it was going so fast and it was out of control, and they were like, fuck it. And they pressed the AZ5 button. Now, AZ5, same as scram, inserts all the control rods. That poisons the reactor, essentially, absorbs all the neutrons that are flying around. Let's go. Crisis averted, right? But in the Chernobyl reactor, the control rods were made out of boron, which we talked about. Boron is kind of a shitty neutron poison. Cadmium is better. You're still going to want to use boron just to be safe. You're going to want to dump a bunch of boron in there, but cadmium is better. So the control rods were made out of boron, which is kind of a shittier neutron poison. And these boron control rods were tipped with graphite. And remember, graphite is a nuclear moderator, and so it speeds up the fission reaction by slowing the neutron flux. Fuck it, we're not going to talk about that. Graphite speeds up the reaction, which is this is what ultimately caused the explosion, was pressing this AZ5 button. Because for a brief second, when those control rods are being inserted, that graphite goes in first, and which infinitely speeds up the reaction, causes the explosion. And so, yeah, that's what I mean when I say that Chernobyl isn't an example of nuclear energy being unsafe. It's an example of Soviets being just so incredibly retarded, dude. You literally could have chosen any other element, to tip those control rods with, and they only tipped the control rods with graphite to save money, right? It's the only reason they did it. And so, yeah, they tipped the control rods with graphite. And so when they press that AZ5, that scram button, and all nuclear reactors have a scram button, like I said, sometimes it's automatic. It was meant to slow the reaction down, right? But you have graphite on there, which speeds the reaction up. On the things that are meant to slow the reaction down, a piece of that actually speeds the reaction up. It's retarded. It's so retarded. Anyone even listening to this would be like, that's the dumbest thing I've ever heard. Why would you even want that at all? Like, forget about Chernobyl and like this retarded nuclear scientist fucking with this reactor, right? Because he was fucking with it. Like, all the xenon had burned off, and remember, xenon is another neutron poison, slows the reaction down. He was like fucking with it. They were trying to do some test on it, and all the xenon had ended up burning off. It had gotten super cold, right? And remember, heat slows down the reaction. And so when they were fucking with this thing, they, like I said, they put it all the way down. They decreased the reaction a whole bunch, and so it was actually super cold. And remember, heat slows it down. And they had like burned off all the xenon, which is another neutron poison. They'd fucked this thing all the way up, right? And there was something with the coolant too. Remember, the coolant like absorbs the heat from the fission. And anyway, they had really fucked it, right? And then the bureaucrats, the Soviets, whoever designed this fucking reactor, fucked it even more. Fucked them by deciding to tip the boron control rods with graphite, which speed up the reaction. Anyway, so it wasn't really even a meltdown. Meltdown, apparently there's no official like parameters of what a meltdown is, but we're going to talk about meltdowns a little bit here. So, meltdowns. Chernobyl, I guess I'll try to wrap up the Chernobyl thing real quick. Chernobyl happened because they tipped the things that were supposed to slow the reaction down with things that speed the reaction up. That's why Chernobyl happened. Also happened because this nuclear scientist decided to fuck with the reactor for some tests that they were doing on it. Ultimately happened, right? The thing that ultimately caused that explosion was that graphite. Graphite's like gasoline, and gasoline floats on water. So let's say you're trying to put out a fire and you have a bucket and it's filled with water, but on top of that water is a layer of gasoline. And so when you go to throw that bucket of water on the fire, for a brief second, the fire is going to get even bigger because the gasoline is floating on top of the water, and so it's going to be the first thing to hit that fire. That's Chernobyl. Okay? I explained that perfectly? I'm a genius? Okay, got it. It's a meltdown. So, heat in a reactor core is usually removed by the coolant, but if the coolant isn't removed fast enough, or if it stops altogether, a meltdown can occur. And so for like a real like full-on meltdown, like we got to close the nuclear reactor down and like surround it by a concrete wall and never touch it again, a lot of shit has to go wrong. And I'm going to tell you about all the shit that has to go wrong. So coolant going through the pipes that surround the reactor. If it stops going through there, then the reactor is going to get super hot, or the reactor core. The core is going to get super hot. The whole thing is the reactor, but the core is where the fission and stuff actually goes on. So, anyway, if the coolant stops going around that, it's going to get super hot. And you're probably thinking, well, then, like, so what? It'll like slow down infinitely, right? Because when it gets hotter, the reaction slows down. But it slows down, but it doesn't stop altogether. So usually when cooling is disrupted, scram is automatically initiated. All those control rods go in, they dump a bunch of boric acid into there. Great. And so it's automatically initiated, and the fission chain reaction immediately stops. But any radioactive fission fragments that have already been created will continue to produce heat. And this is called decay heat. So you have these fission fragments. We talked about iodine 135 and xenon 135. Iodine 135 in and of itself is not a neutron poison, but it turns into xenon 135, which is a neutron poison. Those are two possible fission fragments that can be created. But you can create other fission fragments that are radioactive. And so, radioactive, they're unstable, they're releasing neutrons and stuff like that. And so, more fission can continue to go on. And so, these fission fragments, this is called decay heat. And this decay heat can melt the metal rods that hold the uranium pellets and also melt other structural materials, which will combine with molten fuel to create corium. And so it's super hot, and so it melts, like we talked about. It's a metal rod, and then inside the metal rod is the fuel. That'll combine with like the other structural materials, the other like steel and aluminum, and probably not aluminum, but the other shit they use to make the reactor. And this will all combine together to create this thing called corium. And if you've ever heard of the elephant's foot, if you've ever watched Chernobyl and they talk about it melted through the thing and it was on the floor, that's when they have to bring in the miner guys to create the heat exchanger pad to absorb all the heat so that the elephant's foot doesn't melt through the ground and poison all the water. The elephant's foot is corium. It's basically this combination of molten fuel, molten uranium. That's what they use for fuel. That's what most nuclear reactors use for fuel. So it's molten uranium mixed with molten like steel and all this stuff. And it's super fucking hot. And fission is going on in there. Right? Because inherently with nuclear materials, fission is going to go on. It doesn't have to be in a nuclear reactor because those radioactive materials are unstable. And so neutrons are constantly being released. And so fission is kind of constantly going on with radioactive materials. It doesn't just suddenly start happening when you put it in a reactor core. But anyway, you have this thing called corium, and it's melting. And if all of this happens, the corium can pool and damage the reactor vessel, releasing radioactive materials. So that's like the absolute worst case scenario in a meltdown. Best case scenario is the computer, or ideally a nuclear engineer, sees the temperature going up and is like, fuck, let's just do this shit. I don't care if I get fired. I'd rather get fired for like stopping a nuclear reaction, like a healthy nuclear reaction from going on, than let a meltdown happen. It hits the scram button, boron is released, control rods go in, nuclear reaction essentially stops, and meltdown is prevented. Worst case scenario that can happen. Chernobyl's the worst case, but also for any other country than the Soviet Union, Chernobyl is not the worst case. Chernobyl could not happen in an American nuclear reactor because we don't use a moderator to tip our control rods. Remember, control slows it down, moderator speeds it up. We don't use a moderator element to to tip our control rods, which are supposed to slow the reaction down. So the absolute worst case in like an American reactor would be this, where the corium is created, and then not only is the corium created, the the reactor vessel is made out of a material that the corium can melt through. Radioactive materials released poisons the water and the ground and stuff like that. That's absolute worst case scenario, and which is bad. That's bad for sure. But with Chernobyl, like the air got poisoned with radioactivity, right? Because it fucking exploded. They made a bomb, and so the air got poisoned with nuclear material and stuff like that. The groundwater almost got poisoned with nuclear material and stuff like that. Yeah, Chernobyl was just fucked up. Yeah, but that's hopefully you understand nuclear reactors slightly. If you understand one part of this, you're a genius, because I feel like I did a very poor job of explaining it. But look, I felt like stepping out of my comfort zone for this one. We've been talking about knights a lot, and don't worry, we're gonna talk about knights next week. I think we're doing medieval Romanian warfare, so it should be more intelligible than this episode. But fuck it, is what it is. I hope everyone listening to this has a good day, a good week, a good year, a good life, and I'll see you guys in the next episode. Don't tip your control rods with a moderator. Ping.